1.6 Applications. In algebra, the quadratic formula is defined as the equation for x equal to b plus or minus square root of b squared minus 4ac over 4a for the quadratic polynomial ax squared plus bx plus c. So now let's do an example. X squared minus 2x plus 10 equal to 0. A equal to 1, right? Or a equal to 1. Maybe is this correct? Yes, that's correct. A is equal to 1. Sorry, I was just looking for the page, right? And b is equal to negative 2. C is equal to 10. Well, you write plus minus. Sorry, I think it's negative b. There's a negative b. Negative b plus minus b squared minus 4ac 2a. So that is equal to negative 2 plus minus square root of negative 2 square minus 4. A is 1, c is 10, and all over 2 times 10, right? And well, that gives us 2 plus and minus square root of negative 36, 2, and consider negative 36 is equal to square root of negative 1, square root of 36, that is equal to I times square root of 36 equal to I times 6, right? Okay. So that is 6i, right? And well, we can write, so our complex roots, z1, right, that is equal to, well, 1 plus 3i, and z2 is equal to 1 minus 3i. Notice that z1 is equal to the complex conjugate of z2, right? And z2 is equal to the complex conjugate of z1, right, like that. Now, the quadratic formula works perfectly fine in the complex plane. For the complex polynomial, the complex quadratic polynomial, that is az squared plus bz plus c is equal to 0, and z can be found by performing this quadratic formula, but just in the imaginary plane, negative b plus or minus b squared minus 4ac, and take the square root of that over 2a. Yes, and well, let's do this one. Well, now let's define a is equal to 1, b is equal to, well, 1 minus I, and c is equal to negative 3i, right? And now we form the formula, the calculation, half over 2a is equal to, well, negative, take a negative of that, well, that is 1 minus I plus minus negative 1 minus I square minus 4a is 1, c is negative 3i, right? And all over 2 times 1, right? And 2 times 1, right? And well, that is equal to 1/2 negative 1 plus I, right? And then plus, we have 10i, right? Running out of space, and you take the root of it, right? And 10, 10i, take the root of it, well, really is just r equals to 10, and then you have theta equals to -2, right? Really, because, well, you can't really simplify this anymore. You have I to the, you take the root of an I, right? Well, then what you can do is that you can write it in, the polar form, right? Because this is, you don't really have to simplify it. This is already in the complex plane. This is an integer, really. No, not an integer, but it is a number on the complex plane, right? So now we want to calculate the root. So how do we calculate the root? We usually do it in the manner that involves 0, right? So when we calculate the root, we have multiple roots, right? So how do we do it? We can write this as, well, if we want to find the root, right, that is z1/2, right, is equal to w, then w squared is equal to z, right? Now we recognize that n is equal to 2, right? And that is n equals to 2, so your k is equal to 0, 1, and it goes up to n minus 1, that's 1, right? So now you want to find, see, now it's getting more complicated, because now you have to do the, you have to do the quadratic formula, and then you do simplify, and then now you calculate the root, right? So now w naught is equal to, well, square root of 10, right? That is r squared. Well, no, that's just r, right? And, well, you have multiplied by cosine of pi over 4 plus I sine pi over 4, and that is equal to, well, -10. You have 1/2 plus 1/2i, right? That is equal to √5 plus √5i, right? And similarly, we can do calculate w1, that is equal to, well, if you add 2 pi, right, like k equal to 1, right? So this becomes I sine of 5 pi over 4, that is equal to -10 of 1/√2 minus 1/√2i, right? And that is equal to -5 minus -5i. And therefore, well, we have to find a z, right? So what is a z1 and z2? We did find the root for this, but we didn't find z1, right? So, well, now we substitute it into our original equation. So now we want to get z1. Z1 is equal to 1/2 -1 plus I plus √5 plus √5i, right? And well, that is equal to 1/2. You can perhaps do some simplification, really make it into real and complex, right? So that is √5 minus 1 plus 1/2 √5 plus 1i, right? So that is z1. Similarly, we can do z2. Well, we substitute it in, -1 plus I plus, well, -5 minus -5i, right? That is equal to, well, we can factor out negative sign. That is √5 plus 1 minus √2 √5 minus 1 I, right? So there are our two roots, right? Now, factoring a quadratic polynomial, well, by means of by means of the previous theorem, a quadratic, well, what is this? A complex quadratic polynomial can be factored into the form a times z z minus z1, and then z minus z2, right? So, right. So you have 1, like how we did it. We can put these into this form. Really, it's just that you factor out a, and right. You have a like that, and then you factor it. So now, if we take a look at this one, right? You have, well, x squared minus 2x plus 10, right? And that can be factored into, well, we did earlier, that is minus 1 plus 3i, right? 1 plus 3i, and then multiply that by x minus that, x minus 1 minus 3i, that's that, right? And, well, that is equal to x minus 1 minus 3i, and then you have x minus 1 plus 3i, right? And now we say, similarly, well, we have this, right? Z squared plus 1 minus I, z minus 3i is equal to, well, what is a? A is just 1, right? It's equal to z minus z1, and then you have z minus z2, right? So that is equal to, well, you have z minus 1 over 2, and you have root 5 minus 1 minus root 1 over 2, root 5 plus 1 I, and then you multiply that by the second part, plus minus becomes plus, right? And then root 5 plus 1, and 1 over 2, root 5 minus 1 I, right? That's the imaginary part, and there it can be factored into that. Now, well, on the chapter of variation of parameter, or just let y equal to e to the mx, and, well, may solve the homogeneous differential equations a second derivative y plus b first derivative y plus cy is equal to 0. Well, that is when you write over here, right? And then you take a second derivative, and there's m squared, right? And this is what happens when you substitute y equal to emx, right? And then you can always factor in emx, and then you will end up with this equation, and it's called the auxiliary equation with the assistance of Euler's formula. E to the I theta power is equal to I times theta power, or is equal to cosine theta plus I sine theta. The solution of the second order differential equations may be found in the form with z equal to alpha plus I beta. Then y is equal to, well, y is equal to, oh, sorry, can't remember this is alpha, right? This is alpha. So you have alpha x, e to the alpha x multiplied by cosine beta x, and y2 is equal to e to the alpha x multiplied by sine beta x. So how do we prove it? Well, really, if you can't factor, right, you'll, well, because m is a root, right? M is a root, right? And because it can be factored, but by the fundamental theorem of algebra, there must be 2 roots for this quadratic. So you may write the root as, equal to z, right? And the other root is just the z conjugate, which is equal to alpha minus beta, right? So now, if you want to, well, now you use the Euler substitution. Well, actually, not the Euler formula, not yet. you know, m is a root, right? So m is always over here, but we just said that this is a root, so how about we rewrite it over here, right? So we raise it to alpha plus I beta power x, right? So, well, by the previous theorem, we can, by the theorem we discovered in the last session, we know that we can divide up the complex powers like this, right? And that is equal to, well, we know I beta x. How about we make a substitution? Let beta x equal to u, right? So we can now, or theta, now we can use the Euler's formula. So you can, well, write it as like this, cosine of, well, what was it? Alpha, no, beta x, and well, substitution, right? And then now it's just sine of beta x, right? And similarly for well, the other roots, right, x, so that is just equal to alpha x cosine beta x minus I sine beta x, right? And therefore we can write it as y1 is equal to the sum of these two, right? It's just alpha plus beta x, right? And then you add alpha minus I beta x, right? And then y2 is equal to 1/2. Now you subtract, right? Alpha plus beta x minus e alpha plus alpha minus, sorry, it should be minus I beta x, right? But isn't this just well, isn't this just cosine, and this should be sine, right? Because we know the complex definition of sine, let's say sine theta, right? Sine theta is equal to ei sine theta plus e negative I sine theta, or just the complex conjugate of it, so you can think of it like this, right? But just now we have a b, you have a beta over there. Well, so your y can really just be written as equal to, well, you can write the real part over here, and you have your complex, right? No, your y2 can be written as e alpha x sine beta x, right? Like that. And now let's do a differential equation. Well, if you let y equal to e mx, right? And then you take the derivative, first derivative, that is equal to m e mx, second derivative m square e mx, then you get m square e mx plus 2 e mx plus 2 e mx is equal to 0. Factor out e mx, that is equal to m square plus 2m plus 2 is equal to 0. And your m square plus 2m plus 2 is equal to 0. Well, then your m1 by the quadratic formula, you get -1 plus alpha. Since this is real, you don't really have to do all of the argument and in polar form, no. Well, then your m2 is equal to m1 conjugate, that is equal to -1 minus I, right? And now you may define your alpha as, you know, -1, and your beta is equal to 1, right, by m1, really. So now your first solution is equal to e negative x cosine x, and y2 is equal to e negative x sine x, and then your general solution, I forgot, was it this is general solution. No, sorry. Y is equal to y1 plus y2, maybe like this. You can write it as g, but I will just leave it like that, right? Exponential form of a complex number. The exponential form of a complex number is defined as e to the z power, which is e to the x plus I y power. Well, then we can always separate the power, really, right? And then we can write the I, the imaginary component, into cosine and sine with the aid of Euler's formula, and now it possesses the it possesses the property. Well, if you multiply them together, e to the z1 multiplied by e to the z2 is equal to, if you add the exponents together, right? And now the polar form of the complex exponential is defined as the following, and it's called the exponential form. Well, really, if you remember, this is the polar form, right? And what is this? This is just Euler's formula, really. So you can write it as z is equal to, r times the Euler's formula, which is this, right? Which is exactly what we had. And now, remember this, what is it? To integer power, right? Well, how about we do an example of this, really? Well, let's write it in terms of this form, right? So let's say I is equal to, for example, I is equal to e I pi over 2, because what you did was, e to the 0, because it's the x component, right? And then you have cosine of pi over 2, and plus I sine pi over 2. Well, that is just really 1 multiplied by 0 plus I times 1. That is equal to I, right? So I think of like that. So now, if you have 1 plus I, then now if you find the R, right, you take the square, you calculate the modulus of it, so that's square root of 2, and you'll find the argument of it. Well, you do the inverse tangent, right? So that is equal to pi I over 4, right? So now, if you have z to the 1 to n power, well, that is just, if we take the n root of r and multiply this by I, you can factor in I, you have theta plus 2k pi, and everything divided by n, right? Because this is really just fundamentally this part, right? And for k is equal to 0, 1, 2 to n minus 1, right? So now, consider the problem of finding the steady state of the current IP of time t in the LRC, right? Yes, LRC series, which can be modeled with this differential equation, L times the second derivative of Q, right, plus R first derivative of Q plus 1 over C. Q is equal to your initial your condition, right? And IP is called the steady state current, and QP is the steady current charge. And now let's solve for it. So now you have to assume, with the aid of variation of parameter, I think you can. So you can guess. Well, GP is equal to, well, since E naught is a constant, you will assume that GP will be in the form of sine gamma t plus b cosine gamma t, right? And well, what is your A if you solve for it, right? So if you solve for it, well, I'm skipping a lot of math over here because the book skips a lot of math, because I'm sure you can work it out, right? If you set them equal to each other, right? If you take the derivative and you set them equal to each other, you should solve for a, so you get negative gamma z square plus, well, and b equal to E naught r over negative gamma z square. So now we have to define what z is, because this is not the z we have. No, this is not small z, this is bigger z. So we really have to define what z is. So now we also have x to solve for, right? What is x? How about write it like this, right? X, write it like this. X, right? Well, x is just L gamma minus 1 over C gamma, right? C gamma, this is not R, this is gamma. And Z is just equal to, well, X squared plus R squared, right? And, well, this is called the reactance. And this is called the impedance. Right, of the circuit. And therefore your QP, since now we have solved for your A and B, right? So now your particular solution is equal to negative E naught X divided by gamma Z square sine gamma T minus Z naught R divided by Z square cosine gamma T, right? And since we want to find the steady current, well, you know that di dt is equal to you know that I is equal to dq dt, right? Then if we take the derivative of the particular solution, it should give us the particular solution in what that is, qpt divided by t, right? Divided by dt, that is, well, then your ipt, your steady current, is equal to, well, you take the derivative of this, right? Then you get E naught over z, and then you have q over z, you have sine gamma t minus x z cosine gamma t, right? And therefore your differential equations can be written as L is equal to, well, L not equal to, L multiplied by di dt plus Ri plus 1 over CQ is equal to this. But just a side note, right? Just a side note that this can be written as an integral defined differential equation. Let's say I of tau, d tau is equal to this. So now you have to perform a Laplace, right? Laplace to solve for it. But that is that. Now then your impressed voltage, right? Your impressed voltage E naught sine gamma t, that is equal to, well, imaginary part of E naught e to the j gamma t, right? And therefore your IP is equal to imaginary part of a e j gamma t, right? And now substituting for the result, we get there's just a complex impedance, but well, now let's derive the complex impedance. Well, so assume that the complex exponential satisfies the usual differentiation rule. Use the fact that charge Q is an antiderivative of current I, which is what we did over here, right? And equate the coefficient of EJ gamma t. The result is, well, so basically you want to use this to solve for A, right? You want to so now you're going to solve for this differential equation instead of this. So you have to guess again with your guess what is A, guess what is B, use the variation of parameter, right? And if you work out the math, right, you take the derivative and you equate them together, well, then you get E naught of R plus J. Well, since we define it over here, we set them equal to each other, right? Because now let's take into the imaginary axis. You have, well, L gamma minus 1 over C gamma, right? But of course you don't have to know these things because this is physics, right? But it's just better to know. It's just some applications, right? So we can make a substitution. Isn't this just EX? Isn't this just X, right? So now we know where X is the reactance given in over here in the equation over here. The denominator of the last expression, EC, right? Of EC, well, that is this part, right? So let's call it EC, right? So this is R plus J of this some equation is equal to, well, you make the substitution just to clean it up, right? And now J is J is, oh, I think it's an I. It's just an imaginary number. So now this is called the complex impedance. Complex impedance, right? And since the modulus of the complex impedance is, well, if you take the modulus of this, it's equal to, well, R squared plus, really, how about I just write it as X squared? But you know what X is. X is this big thing, right? We see that the impedance of Z and the complex impedance Z relates. That is, Z is equal to the modulus of C, right? So basically you took the complex impedance by means of modulus. You can relate them together, right? So they're really the same thing, but now you just, complex impedance is just that you take into the complex zone, the complex plane, right? And now how about we write this as, well, ZC is equal to, well, the modulus, right? And then you want to make it into the polar, you want to write it into the polar representation, right? So this equals R E J theta, right, in this form, right? So, well, but we just said that they are equal, right? If you would compare this one and this one over here, they are the same. So how about we can write this into Z, right? Z of E I theta, right? And now we want to find the relationship of this. Well, you want to find tangent theta, right? Or that's just the angle between it, right? So you want to solve for tangent theta. Well, that is just really just x, but over c over r, right? So hence your a is equal to zc, right? This part, right? Equal to zc because you have j, this part, this is ijx, right? So right. So if you take the modulus, this is that, right? They're the same. And now, well, I'm not very good with physics. Anyway, so how about you write this into z naught, right? And you have z in the bottom. No, you have e naught and you have z naught, and you have e naught on the top, and then you have z I j theta, right? So your steady current, steady state current, but it's just steady current is equal to this is equal to the imaginary component of e naught over z, and you have e minus j theta, multiply that by j gamma t, right? And now we're finished.